Howdy guys, it's Rock Papa. Hope you guys are doing great and enjoying this fabulous fall weather we're having. Today's topic is metamorphism. We're going to talk about what metamorphism is, how it occurs, the different kinds of metamorphism, and I'm going to give you rock examples of before and after metamorphism for a huge pile of rocks in pictures. So stay tuned for that. If this video is good, please subscribe, and thank you so much for all those who have subscribed. So here we go, metamorphism.
Metamorphism is the change in rocks due to a combination of heat, pressure, and hot fluids.
Yes, my wonderful friends, metamorphism is caused by subduction and the continental collisions that result from subduction.
During metamorphism, the elements in a rock don't usually change, but they reorganize to form new minerals.
When an igneous or sedimentary rock is subjected to a drastic change in heat and pressure, its minerals become unstable because they do not like that environment. And so the elements in the rock reorganize into minerals that do like that heat and pressure environment. And the rock becomes a metamorphic rock.
There are three kinds of metamorphism I am familiar with. The first is prograde metamorphism. I call it forward metamorphism. And that is when an igneous or sedimentary rock is subjected to an increase in temperature and or pressure. The next kind of metamorphism is retrograde metamorphism or reverse metamorphism. That's when a metamorphic rock is subjected to a decrease in temperature and or pressure, and it kind of goes back toward its igneous version, but of course not all the way back. Water is almost always present in retrograde metamorphism, and it has an effect on the rocks. And finally, there's hydrothermal metamorphism, also called hydrothermal alteration. And this kind of metamorphism is caused by superhot fluids that have been affected by volcanic activity. Usually we're talking about superheated water that contains any number of minerals like gold or sulfur or lead or zinc or something like that.
Okay, rock buds, now let's look at examples of these three kinds of metamorphism in pictures.
Let's look at some examples of prograde metamorphism. This is volcanic tuff, the quartz-rich and potassium feldspar-rich material that is blown out of a stratovolcano. The increase in temperature and pressure associated with metamorphism basically fuses the quartz, and you get the metamorphic rock metatuff. Here we have a sample of granite, a quartz-rich felsic intrusive rock with lots of quartz and potassium feldspar and some sodium-rich feldspar. And this is dacite, the above-ground version of granite. Increase in temperature and pressure causes the light and dark minerals to separate into metamorphic bands, giving rise to granite gneiss.
Hey guys, you probably have figured out by now that metamorphism cannot do a whole lot with quartz. That's because quartz has the highest melting point of all minerals, and it's also has very, very strong bonds. So metamorphism can fuse quartz grains and maybe separate quartz into bands, but that's about all it can do with quartz. It's not going to change it into another mineral very easily.
Okay, here we have diorite pluton and its above ground equivalent andesite lava. Biotite mica is a prominent mineral in these rocks. These are intermediate reaction rocks, somewhere between quartz-rich felsic rocks and iron and magnesium-rich mafic rocks. Once again, metamorphic pressure causes the light and dark minerals to separate into bands, giving rise to the metamorphic rock biotite gneiss. Here we have gabbro, an intrusive mafic igneous rock. And here is diabase, which has the same minerals, another intrusive rock that's emplaced as magma fairly close to the surface. And here is basalt, the above ground equivalent of gabbro and diabase. Prograde metamorphism usually turns these rocks into amphibolite. Can you see the little pinky red spots in this rock? That's garnet, and it is an indicator of medium to high levels of metamorphism. Here's an amphibolite close-up showing the platy white crystals of calcium-rich feldspar. Now let's look at prograde metamorphism in sedimentary rocks. This is sandstone, a sedimentary rock that's formed from sand grains that are mashed and glued together. The heat and pressure of prograde metamorphism usually melts the sand grains and fuses them into a kind of glassy metamorphic rock called quartzite. And here we have a sedimentary rock called shale, which is made of tiny particles, mostly of clay minerals, but also tiny particles of quartz. Clay minerals probably started out as potassium feldspar and muscovite mica and maybe biotite mica, and the processes of erosion and weathering added water to them and turned them into clay minerals. Heat and pressure of metamorphism turns shale into the metamorphic rock slate. Shale can usually be scratched with your fingernail, but you have to have a nickel coin to scratch slate. If you metamorphose slate, it turns into phyllite. Phyllite is harder than slate and shinier because the clay minerals are being transformed into muscovite mica that begins to shine. And of course, phyllite is a metamorphic rock. The final stage in the metamorphism of clay minerals is called schist. Schist is harder than phyllite and made of even more hunks of tightly compressed muscovite mica. And you see those little garnets? They're a sign of medium to high levels of metamorphism. Oftentimes, hunks of mica will slough off from the schist and form what I call schist pennies. Most geologists call these button schist. You find lots of these schist pennies, especially in strike-slip faults like the Brevard Fault Zone. They get into the streams and look like treasure. Now let's look at the sedimentary rock limestone. It starts out as shells and hunks of coral reefs that get mashed down on the bottom of the ocean. As the layers build up, the weight of the compaction obliterates the shell's structures, turning them into calcium carbonate. But at this point, it is still limestone, a sedimentary rock. Here is dolomite, a sedimentary rock that is very similar to limestone. As a matter of fact, it usually forms from limestone by the chemical addition of magnesium to the calcium. So it's magnesium calcium carbonate. Prograde metamorphism turns both limestone and dolomite into the metamorphic rock marble. So beautiful. And as you guys know, limestone, dolomite, and marble will fizz in 7% hydrochloric acid solution. A good test. We're now in the Pennsylvanian and Permian time, when eastern North America was a giant sandy coastal plain covered by swamps and rivers and fern-like forests. These forests were covered by layers of mud and eventually they were pressed into bituminous coal, which is a sedimentary rock. During the Akkadian orogeny and then the Alleghenian orogeny, the layers of bituminous coal were pushed up into folds and faults that metamorphosed them into a high-grade coal called anthracite coal, which is a metamorphic rock. Okay, guys, now let's talk about retrograde metamorphism, which is metamorphism in reverse. Here are some examples of schist, a metamorphic rock that contains a whole bunch of muscovite mica. In the presence of water, and oftentimes hot water, the schist can undergo reverse or retrograde metamorphism, where the muscovite mica is transformed into cerussite. This is caused by the presence of water. It could be groundwater or ocean water, and it doesn't have to be hot, but often is. Cerussite is a whitish, silvery version of muscovite, with a little less potassium and aluminum and a little more silica than muscovite. Here's some biotite schist, a metamorphic rock similar to the muscovite schist, and it can also undergo retrograde metamorphism, and when that happens, the biotite is transformed into chlorite, a greenish mineral. And the new metamorphic rock is called a chlorite schist. Here is a funky hokey pokey man's skull carved from chlorite schist. Ocean crust covers most of our globe, and it is very deep down under ocean sediments. It's made of gabbro on the bottom, basalt on top of that, and the basalt is arranged in these columns that they call a sheeted dike complex. During continental collisions, ocean crust is very often shoved up on land so that its temperature pressure regime is drastically changed. Lots of ocean water is involved in this process, and it can cause the basalt to retrograde to a metamorphic rock called green schist. Metabasalt is another name for this rock. In this example of metabasalt, the black hornblende and pyroxene have been retrograded to biotite, and you can see a streak of either chlorite or epidote, alteration minerals. Here's an example where the dark minerals have retrograded to biotite and chlorite. And here's a piece of catoctin greenstone where the dark minerals have retrograded to chlorite and likely epidote. This is peridotite, the rock that's located underneath ocean crust, and it's the rock of the molten plasticky mantle, the most abundant rock on Earth. Peridotite can also get shoved up on land along with ocean crust in continental collisions, and when that happens, it is transformed into soapstone and serpentinite. Both soapstone and serpentinite are soft. You can scratch them with a thumbnail. That's because in the process of retrograde metamorphism, water has been chemically added to the peridotite. And this is asbestos, yet another form of retrograded peridotite. Let's look at a couple of examples of hydrothermal metamorphism, and then we're done. This is a volcanic island formed by the subduction process. Its stratovolcano is belching out that yellow stuff, which is felsic volcanic tuff, and this volcanic tough material will settle down on the underwater flanks of the volcano, where it will be flushed with hot volcanic water, hydrothermal solutions that contain all kinds of minerals, gold, silver, etc. This black smoker at the bottom of the ocean is producing hot hydrothermal fluids that will flush through the tuff and change it into quartz, muscovite, cerussite, pyrite, schist. The hydrothermal fluids leach out some of the elements, while adding elements like gold, sulfur, silver, lead, zinc, copper, etc. This is Grays Mountain, located in Piedmont, Georgia. It's a hydrothermal system that was part of the Carolina Supertrain that was attached to the eastern United States during the Acadian orogeny. Hydrothermal processes associated with the Carolina terrain volcanoes produce very interesting metamorphic minerals like kyanite, lazulite, multicolored iron deposits, and titanium oxide, which is called rutile. Okay, most excellent rock buds, that's it for Metamorphism. This has been a pretty long video, but I wanted to cover it as thoroughly as I possibly could for you guys. So hopefully this has been useful. If so, please subscribe. And this is your Rock Papa saying, happy rock hunting. Papa out.